Hello everyone. In today's lecture, we will see some theoretical results related to series. So, let me first define Cauchy criterion for convergence of a series. Okay. So let me state the result. So consider a series summation an. The series summation an converges if and only if for every epsilon greater than 0 there exists a knot in N such that for every Mn greater than or equal to N naught, mod of Sn minus Sm is less than epsilon. Okay. This Sn minus Sm, Sn is our sequence of partial sums. So this will be Ak, k going from 1 to N minus sum over Ak, k going from 1 to M. So this is less than epsilon, which is same as saying mod of Am plus 1, Am plus 2 and so on, An should be less than epsilon. Okay. So what we are saying is that after a certain N, sum of all the remaining terms should be less than epsilon. Okay. So let us prove this. So we are saying that the series converges if and only if this happens. Okay. So first, suppose the series converges. Suppose summation n converges. This means that the corresponding sequence of partial sums converges. This converges. So this means Sn is a convergent sequence, and because Sn is a real sequence, this implies Sn is a Cauchy sequence, which is nothing but our definition of Cauchy criterion, that is summation an satisfies Cauchy criterion. On the other hand, if I start by saying that summation n satisfies Cauchy criterion, so this is second part of the proof. So summation an satisfies Cauchy criterion. This would imply Sn satisfies Cauchy criterion because it is actually in terms of Sn. So this would imply Sn satisfies Cauchy criterion, and this would imply Sn is Cauchy because Sn is a real sequence. We have proved that a real sequence is Cauchy if and only if it is convergent. So this implies Sn is convergent, and therefore summation an converges. Thus, the series is convergent if and only if it satisfies Cauchy criterion. Okay. Let us now introduce a couple more theoretical results. So when we say a series is convergent, what happens to nth term? Okay, so we will have a result related to that. So if summation an converges, then an, that is nth term, must go to 0. Okay, this is kind of obvious. Okay, why? Because we are saying series is an infinite sum, and that sum converges to a certain value means the later terms do not add much to the original sum, so they must be going to 0, because otherwise the sum will not remain constant, otherwise the sum will keep on changing. Okay, so let us try to prove this. What we know is summation an converges, so summation an converges, this implies the corresponding sequence of partial sums converges, corresponding sequence of partial sums converges. Okay, therefore the sequence is Cauchy. Therefore the sequence Sn is Cauchy. What is meant by the sequence being Cauchy? Given epsilon greater than 0, there exists a knot in n such that mod of Sn minus Sn is less than epsilon for every mn greater than or equal to n naught. In particular, I could take mod of Sn plus 1 minus Sn is less than epsilon for every n greater than or equal to n naught. Okay, because m is n plus 1, and this is same as saying mod of an plus 1 is less than epsilon for every n greater than or equal to n naught, and this is equivalent to saying an converges to 0, because given epsilon greater than 0, we have found n naught such that mod of an minus 0 is less than epsilon for every n greater than or equal to n naught. Okay, another way of approaching this proof is I could write an as Sn plus 1 minus Sn. Okay, and then because summation n converges, I know Sn converges, so if I apply limit throughout, then I'll get limit an equal to limit Sn plus 1 minus limit Sn, both these converge to same point, so this is 0, and hence limit an is 0. Okay, this is another way of approaching the same result. However, remember that converse of this result is not true. In the earlier lecture, we have seen that the harmonic series is divergent. Harmonic series is summation 1 by n. It's a divergent series. But we all know that 1 by n goes to 0. Okay. Hence, converse of this result is not true. That is, if an goes to 0, that does not necessarily mean that the corresponding series summation an converges. Okay. Now, let us introduce one more term, that is tail of a series. Okay, so this is actually kind of a generalization of what we have been doing. What is tail of a series? So if a series is convergent, then what it means? It means that summation an is some finite number s, correct? So what we can do, we can split this summation an as summation n going from 1 to n naught, that is first finitely many terms, plus summation n greater than or equal to n naught, and we are saying that this is equal to s. Okay, everyone okay up to this point? This means that summation n greater than or equal to n naught can be defined as s minus sum over n going from 1 to n naught an. Okay, so this part, summation n greater than or equal to n naught an, this part is known as tail of a sequence. Okay, and we are now going to show that this, again, tail of a series converges to 0. Okay, let me state the result, then we will try to prove it. So suppose summation an is a convergent series, then summation n greater than or equal to n naught an, this converges to 0 as n naught goes to infinity. Okay, tail of the series converges to 0 as n naught goes to infinity. So how do I prove this? We will again use definition of convergence via convergence of partial sums. So summation an converges implies that the corresponding sequence of partial sums converges. Okay, therefore given epsilon greater than 0, there exists some n naught such that the sequence is Cauchy, that is such that Sn minus s is less than epsilon for every n greater than or equal to n naught, which implies Sn belongs to s minus epsilon to s plus epsilon for every n greater than or equal to n naught. Okay, in particular Sn naught also belongs to s minus epsilon to s plus epsilon, which means that s minus epsilon is less than or equal to Sn naught, okay, and S minus Sn naught, that this would imply that S minus Sn naught is less than or equal to epsilon, okay. And what is S minus Sn naught? If I look at this is S and this is nothing but Sn naught, okay. So we get that S minus Sn naught, which is equal to summation an n greater than or equal to n naught, this becomes less than epsilon, okay. Hence we have proved that for a convergent series its tail part converges to 0, okay. Now we will go for some algebra of convergent sequences, algebra of convergent series. So if I have two series which are convergent, can I say their addition or subtraction is convergent? So algebra of convergent series, okay. So suppose summation an and summation bn are two convergent series, then what does it mean? It means that the corresponding sequence of partial sums, suppose I denote by Sn the sequence of partial sums for an, and by Tn the sequence of partial sums for Bn. Then summation an is convergent would mean Sn is convergent to S and Tn is convergent to T, because summation Bn is convergent, and summation of An plus Bn, the corresponding sequence of partial sums will be Sn plus Tn. Hence by algebra of sequences, if Sn converges, Tn converges, then Sn plus Tn converges, and hence summation An plus Bn also converges, okay. Similarly, if I have some constant lambda, then lambda times summation An will converge to lambda times S if summation n converges to S. This can also be easily proved via our sequence of partial sums, because Sn will converge to S implies lambda Sn converges to lambda S, okay. Thus addition of two convergent series is convergent, and scalar multiplication of a convergent series gives us another convergent series, okay. Let me now state one more theoretical result related to series. It is again a very simple result, but it is quite useful. So the statement says, if a series is absolutely convergent, then it is convergent. So if a series summation mod an converges, then summation an also converges, okay. How do I prove this? We will again construct Cauchy sequence of partial sums. So let Sn be a sequence of partial sums for summation an. So we have to prove Sn converges, using the fact that summation mod an converges. Okay, so if I want to consider Sn minus Sm to prove that it is Cauchy, because we know that in real line Cauchiness is equivalent to convergence. So this will be equal to am plus 1 plus am plus 2 plus an. Okay, so this is equal to modulus of summation ak k going from m plus 1 to n, and this is less than or equal to, by triangle inequality, summation mod ak k going from m plus 1 to n. Okay, but what is this? This also has some meaning. So what I know is summation mod an converges, so corresponding sequence of partial sums also converges. So for example, T1 is mod A1, T2 is mod A1 plus mod A2. So by this logic, Tn is mod A1 plus 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 mod An. Okay, and hence this becomes now Tn minus Tm. Okay, further, since my Tn is a sequence of partial sums corresponding to a series of non-negative terms, because modulus is non-negative, it's an increasing sequence because mod A2 is always going to be larger than mod A1. So Tn is an increasing sequence, hence Tn minus Tm is positive. But we know that the series mod summation mod an converges, so Tn is a Cauchy convergent sequence, hence it is Cauchy, and hence Tn minus Tm is less than epsilon, or it converges to 0. Therefore mod Sn minus Sm is also less than epsilon for every mn pair greater than or equal to n0. Okay, hence we have proved that if a series converges absolutely, then it converges. So absolute convergence is a stronger result compared to conditional convergence. Okay, so let me stop here for today. Thank you.